Okay, YouTube, in this video I'm going to introduce the imaginary unit I as well as the concept of what we call the complex number system. So let's go ahead and consider this equation here, x squared equals -1, before we get into the complex number system so that we can define the imaginary unit I. So considering this equation, x squared equal -1, we're really asking, what number when taken times itself do we get -1 for an output? And as a matter of fact, we can think of no real number solution to this, because if you took a -1 times itself, you'd get +1. If you took a +1 times itself, you get a +1. So since there is no solution to this equation, what we do as mathematicians is we introduce the concept of the imaginary unit, and we refer to this as I. And what I want to start with is this. I is just shorthand for what we really say that I stands for, which is I is equal to the square root of -1. And I is unique in that it is the only number on the planet that when we take it times itself, you get a negative output. That is to say, if I take I times I, recall that we have just defined I as being the square root of -1. And if I take the square root of -1 times the square root of -1, we actually get the square root of -1 times itself. When I square this radical quantity here, I just get what's on the inside. So it is unique in that it is the only number when squared or taken times itself, we get a negative output. So that being said, since we've introduced this concept of I, what it really allows us to do is start to evaluate expressions such as the square root of -9. And this is just an example that I'm writing here. But if I were to say, let's evaluate the square root of -9, remember, because of our product rule, we could rewrite this as the product of two factors in here. I could say this is the square root of -1 times 9. And we could see that this is the same thing as the square root of -1 times the square root of 9, which is in and of itself the same thing as I times the square root of 9, and we get the square root of 9 is 3. At least the principal square root of 9 is 3. So we can say that 3i would be the square root of -9, whereas if I were to just take the square root of 9, I want everybody to notice that you just get 3. So really, you could see how this process could be completed for any negative value in here. We could say if this was, negative the square root of -5, we could say that this is the square root of -1 times 5, which is, square root of -1 times the square root of 5. And I have no perfect roots in this case, but I could say that this square root of -1 is I, and I get I root 5. So basically what I want everybody to see is that when you evaluate, say, the square root of a negative, all we need to do is really just put an I out front, and what that does is it causes our radicand to switch its sign to being positive. And then we just treat it the same way we do, in simplifying any other radical expression. So square root of -5, well, we'll put the I out front, it becomes I times the square root of +5. So this being said, I do want to check this very quickly. Do we get, when we square this 3i again, if I take this and I square it, would I get back to this -9 that I started with? And the interesting thing is, I'll use my power of a product rule here that says I would get 3 squared I squared, which is the same thing as 9i squared. And recall that we just accomplished this task. The square root of -1 is I, well then I squared is equal to -1. So 9 times I squared really is 9 times -1, which is -9. So again, we get that negative output by stationing an I in there, the imaginary unit. So what causes us to have what we call the complex number system? Well, what I want everybody to notice here is this. We say that complex numbers, when we add real numbers to imaginary numbers, we give rise to a new number system. We refer to this as the complex number system. So anyways, we can look over here to the right. We say complex numbers really are just some A plus some BI part, where we're going to refer to A as the real part. We're going to say A is the real part of this number. That's the real number that we're adding into this. And if we add that to an imaginary number, here we say the imaginary part is the B part. Okay, that's the B part. I don't include the I in that, I just say the B part. But when you glue those two things together, they are not like terms, they cannot go together, but we say it gives rise to the complex number system. So basically, if you take all the real numbers here, we could look at the real numbers as being a complex number where the B part of the imaginary part is 0. So that is to say, if I were to look at the number 3, 3 really is part of the complex number system, because I could relist this as 3 reals plus 0 imaginaries. Whereas imaginary numbers really are these complex numbers, A plus BI, where B doesn't equal 0, but I could say, well, where maybe A equals 0. And if A were equal to 0 here, I would say then I have 0 plus BI, and I get this imaginary number right here. So just know that all real numbers and imaginary numbers coming together form the complex number system, but at the same time, every number you can think of is a complex number because it can be written as some real part plus some imaginary part. So let's kind of expand our definition here a little bit, not a lot. We say the set of all numbers in the form A plus BI. Okay, this is called the standard form of a complex number. Okay, and when you hear standard form of a complex number, of a complex number. We really mean just listing this number in the a plus bi form. But we say the standard form of a complex number is a plus bi with real numbers a and b. So the a and b part, those are actually real numbers. And the I, that imaginary unit I, is glued onto that second real number there, b. What we say is called the set of complex numbers. We say the real number a is called the real part. We listed that on the other page. We say that the real number b, okay, is called the imaginary part of the complex number. So we say a plus bi is our complex number where we have a real part combined with an imaginary part. So we say if b does not equal 0, we say then the complex number is called an imaginary number. So they leave the door open for calling this one an imaginary number as well. They say as long as b doesn't equal 0. What I want to kind of bring up is the fact that if an imaginary number in the form bi has an a part that is 0, that is to say if this right here has an a part that's 0, if a equals 0, then we say that it's called a purely imaginary number because it completely lacks a real part, okay? Whereas if I were to say now, and they don't list this up here, but if the bi part is 0, if I were to say a plus bi if thinking b already, if b equals 0, then we could refer to that as a purely real number. So looking down here, these are just some examples of complex numbers all written in standard form of a complex number. But we say negative 4 plus 6i, we have a is this negative 4 here, that's our real part, whereas the b, is our imaginary part. So we say the imaginary part is just the 6. We don't include the I in that statement. We say the 6 is the imaginary part. But we say the whole thing is this complex number where we've combined a real with an imaginary now. One other thing we want to look at, or two other things we want to look at are, in this instance, we have some purely imaginary number, okay? So if I were to say 2i, why is it purely imaginary? Because we say the real part of this really is 0. And second of all, I could say that this over here, we could say that if I wanted to write 2i in standard form, we would say 0 plus 2i, okay? Likewise, if we had 3 here, we would refer to this as a purely real number. We notice that because its imaginary part, b, is equal to 0. So we could say that 3 really is a complex number. It's 3 plus 0i, but we'd say that it's also a purely real number. So before we finish this video, there is one comment that is worth making here, but we say that when two complex numbers are equal, that is some a plus bi is equal to c plus di, this can only be true if their real parts are the same, exactly the same, and if their imaginary parts are exactly the same. So for instance, if I had a number x plus yi, and I said it's equal to 2 plus 3i, then we would be able to conclude that this can only ever be true if x is equal to 2 and y is equal to 3. Okay. So in the next video, we'll look at operating with complex numbers.